Thanks, Alex, so much for putting this together. It's great to be here again and hear everybody's stories about using Clojure, and also to tell my own. So I know everybody's got the same question, which is, what's going on with the hair? And so somebody told me if I grew my hair like this and got a phone booth, something interesting would happen, but I still haven't found the phone booth. But no, seriously, I'm trying to get into the Foo Fighters, but they haven't called me back. So today I'm going to talk about Datomic. It's a database that we built in Clojure. And I really want to talk about the ideas inside Datomic. It's not really about showing code or trying to sell it or anything. And I'm going to talk about it from three perspectives. First, what problems were we trying to solve? The second, what are the solutions to those problems, sort of in the abstract? And third, a little bit about how we implemented those, and then a little summary. So in terms of problems, of course, all the problems turn into the same problem at some point, right? Which is dealing with complexity. And when I was first working on Clojure, my first year or second year on Clojure, I found this paper, and it was very inspirational. It's called Out of the Tar Pit, and the authors, had sort of pegged the set of problems that I had also pegged. We're dying with this complexity, and most of the complexity is caused by state and the way we manage state or fail to manage state. And they also identified control as a source of complexity. And by that they meant sort of imperative programming or even functional programming being too explicit about control. And this paper was really inspiring. It actually was the paper that caused me to stick to my guns and make Clojure immutable by default and all the data structures immutable. I mean, I had all kinds of ideas in the air, and I was right on the edge. But when I read this paper, I'm like, well, let me just do it. And so I credit it as very much an inspiration. But there's a lot of challenges in the paper. It's not a paper with answers. It's really a paper that poses a problem statement. And they proposed functional programming and declarative programming as expressed by relational algebra as sort of a recipe for getting out of the tar pit, writing programs that were easy to understand, that were fundamentally simple, that were free of the complexity of both state and control. But there's this problem with the paper. It gets to this point where they talk about, there's this state which you're going to interact with relationally, and then maybe your program gathers information or produces information, and then it goes back. And like this state, it magically appears and it magically can get changed. And the paper really doesn't address it at all. It doesn't even propose answers. It's just like somehow this could get updated. And for me, that's this throbbing problem, because this is really where we end up. If we adopt a functional programming language or a functional style of programming, we're still stuck with process. Right? We have some constructs in Clojure for dealing with process, but in the end, usually process produces information. That information has to go somewhere. That somewhere is the database. And then the program has to get it back out of the database and start dealing with it. And that interaction of process outside the system and back is really a problem. It's, everybody who's working in Clojure still knows how nasty it is to try to deal with the database. So Datomic is about closing the loop and solving the process problem. Another problem we're trying to deal with is the lack of declarative programming. And we've already seen this situation improve now, right? We have Cascalog, we have core logic. That kind of stuff is really important, because declarative programming and logic programming is just another level up from functional programming. It's another further abstraction away from how to do things and a concentration and focus on what you want to accomplish, what the problem is. And right now, most people, if they do declarative programming at all, they only do it when they write SQL. Right? It's something that's over there. These servers know how to do this. They have these declarative languages. And they're very powerful. They're much better at manipulating data than our programming languages, including languages like Clojure. They're another level higher. You don't typically write by hand a parallel hash join. But a database server, when given some declarative commands, does it for you all the time. So there's a lot of value there. But again, one of the problems with all logic languages traditionally is they have this notion of an ambient basis. In other words, I'm going to issue a query. Against what? Where is that stuff? How did it get there? And when you look at it again, will it be different? And how do you know when it's going to be different and why? And can you go back to something? Prolog, Datalog, all these languages didn't really focus too much on the data side. They focused on the query side. And even the query languages we have, again, don't really focus on the data side. So how can we give this kind of programming a sound basis is one of the problems we're trying to solve. In addition to the declarative programming being over there, we have a general problem with stuff being over there at all. Client-server programming has a ton of built-in limitations that often you don't really get to see. The first is this basis problem, right? If I issue 2 queries in a row against a server, what has happened in the interim? You have no idea. You have no way to recover the same basis for asking 2 questions, which leads to all this fear, right? You're afraid of issuing multiple round trips, so you try to pile on like everything you might want to know into this request. The other thing is, even to read anything, you have to send it over there. So you end up with very complex queries in order to, in one shot, get everything you might need, and those queries burden these servers. So you're afraid also of overloading them. And you see it in little ways you don't even recognize. Like in SQL, you'll often ask a query, and part of the query is actually answering your question. You know, which records satisfy these constraints? And another big gob of your query is about pulling out the fields you want for your reporting job, because you want to get it all done in one round trip. Those two things have nothing to do with each other. You've just glommed them all into a query because that's how client-server works. So can we do that better? The other thing we're looking at trying to solve is how do we embrace some of the advances that have been made recently in making scalable systems that are arbitrarily scalable and distributed. And a question I had was, what's possible? How much of that, the goodness of something like Bigtable or Dynamo can we leverage without giving up consistency? Because I think consistency is really important. If you don't have consistency, you've now taken on a huge boatload of additional complexity. There are definitely cases in which you have to make that trade-off. You say, I need arbitrary right scaling. I'm dealing with huge data. I'm going to have to make this trade-off. And that's why these systems were built. But these systems are full of cool research and capabilities that don't necessarily have to be applied to the problem that they were designed around. So can we get some of the best of both worlds? Can we get consistency? And if we do, how much scalability can we get at the same time? Another advantage of these kinds of systems is their elasticity. They, as a rule, tend to not be driven by pre-configuration, but they're much more dynamic. So that dynamic nature is something also we'd like to get. I think everybody who pursues a database other than a SQL database partially is looking for some more flexibility in data representation. Everybody's tired of the rectangles and the rigidity there. And people want to do sparse data. They have irregular data. They have hierarchical things, and so document stores have become popular for doing that. Multi-valued attributes are particularly nasty, and everybody would like a nicer way to do that. I think the biggest thing you want, though, in pursuit of flexibility is long-range flexibility. Right? Day one flexibility is straightforward. I use this document store. I can stick anything in it. Okay, that's great. That seems flexible. But flexibility isn't, this isn't flexibility. Flexibility is moving, right? So now time passes. You have to remain flexible. And that's where you can trip up. Because if you've encoded any structure at all, and that could be a set of tables or what you've chosen to put in a document, you've now got this structure that your future changes needs to contend with. And that structure is something that's impeding your flexibility to change your system and to move it forward. So I call that pervasion of structural rigidity. Does it get into your program, make your program harder to change? And another thing we'd like to solve is the time problem. In general, I think databases don't actually deliver the words they claim to. They claim to be storages of memory and to have records. But before computers, these things had meaning that was a lot stronger than the meaning we deliver typically. Right? When we remember things, we actually remember them. We don't replace, our old phone number with our new phone number in our head in the phone number spot. memory is something that you keep around, and records are something that you keep as well. Many, many systems have to do this. Many systems that don't have to do it would like to be able to do this because it really gives you a lot of power. You can audit things. You can potentially look at different points in time. You can really keep track of what's happened. I mean, how many people have ever worked in a system where it wasn't really working that well, and then more data got into the database and it started working? And no one could ever figure out why, and no one ever bothered to go back because they actually couldn't. Hands. Yeah. I mean, this is what it's like. So could this be better? How can we leverage time and actually get it right? And finally, the last problem is how do we incorporate perception and reaction? That was another big part of the tar pit paper was building systems that were reactive, that somehow knew when there was novelty so they could act upon it versus having to poll. Right? And this is something that's really difficult to do. I mean, some databases have stuff built in. You can set up an event system or a queue system alongside to sort of get events. But in general, there's this sort of inversion problem you have where all you know about change is that it's happening over there. And if you really want to know that change happened, you have to go look over there, and you have to keep looking over there. And so we'd like to do that without polling. On the other hand, ideally, perception is a consistent thing. Right? When the light bounces off of you, barring some really nasty interference, what you get is a pretty stable view of what happened. And that stability, that consistency of perception is another thing that's really important if you want to build a decision-making system on the other end. So we'll just, again, sort of go through the same points and look at how to do it. This is what we're trying to get to. We're trying to make applications that are really empowered. They're empowered to perceive what's going on in the world. They're empowered to react to the things that are of interest to them. They're empowered to remember anything that's of interest to them and to make their own decisions. And the idea behind Datomic is, can I design a system that does this, and what do I need minimally under the hood to facilitate this? Because it's pretty easy to understand what you'd want in the peers, but what do you need underneath that to make that go? And that's glommed together right here as something I'm calling coordination services, but I'll split that out later. So the first thing we have to do is really get coherent about what we mean when we say state. And this is the problem now. We're trying to incorporate process. And we know how to do state, in a program, right? We have values. A value is great. Okay, but then we know time passes and there's another value. When you want to put that in a database, what are you going to do? Traditionally, databases have replaced things in place. I'm going to call that place-oriented programming. And there's a lot of negative aspects to that. We need a different idea. We want to try to preserve the tenets of functional programming. But what does it mean to have a value that changes? Well, one way to think about it is if it only changes by expansion or accretion, like these. Can you see the tree rings back there? I wasn't sure how subtle. Those are tree rings. So tree rings, right? They just keep going out. Right? The inside is still there. Right? It's like a value that gets bigger, but it never actually changes in place. So there's this in-between world, right? There's stuff, and then I change the stuff. That's update in place. And like what happened, who knows? It was all over itself. And then there's stuff, more stuff. That's actually pretty easy to understand because if I knew this and then you said that, it's like, okay, this plus that. I have this. I can get a grip on that as a value. There's a more complex way to talk about this, which is the value extends over time, and you're just discovering it as time passes. It's like, was it StarCraft? Like you move and then you see more of the map. Right? So you just run your business more and you see more of your database. It's a way of thinking about it. Although my wife warned me about the determinism problem of saying that, and now I've said it. But the fundamental idea is that the past doesn't change. That gives us something we can hook onto and build on top of. It's not exactly a value. It's not like 42. I mean, 42 doesn't get a little bit bigger. But it's a new notion of a value where the core of it remains intact, and all you can ever do is sort of grow it. When you think about it this way, you realize a few things right away, which is that process Right? And process is what I mean by either genuine novelty, there's new information in the world, or what we would consider updates. Right? But the word update is kind of bizarre. Right? If you have a new phone number, you didn't actually go to your other phone number and change some of the numbers, right? It's not really update. We think of it as update because we're associating with the same attribute of the same entity. But it's actually novelty. So process is about novelty. When you take this idea of state, you realize the first implication is new state means new space. We have to get new space. Now, I don't think anybody with a tree in their backyard is worried about the trunk size of the tree, overrunning their house, right? There's actually not that much novelty in the world relative to whatever's already there, right? No one's growing their business at 10x per year or anything like that for an indefinite amount of time. So we're going to say we're going to accept that process requires new space. It's a given. It's like when I said I want persistent data structures. That requires garbage collection. You have to sort of make that decision and say, okay, I'm going to accept that as a given, and then design a system from there. The other thing that's fundamental is we have to move away from places. Places destroy this entire idea. There's no way to have places and this idea of a value. So let's talk about process now. So process is about novelty. There's either new information or information has changed, right? This is the way you say changed. It requires 4 fingers. It's the same thing, change, right? The first thing you need to do with process to build this system is to reify it, right? You need to make a thing out of it. What happens in an update in place system, right? You look at the world and it's like this, and you look at it later and it's like that. What happened? Where is what happened? It's gone. It's just the effect of a bunch of independent things. It never really had a life of its own. And so what we want is we want to reify process. We want to make it something that we could hold on to, touch, pass around. There's tremendous value in making novelty concrete. And so we're going to do that. The other answer to the process thing is that you need to find some representation for novelty. When people hear about new information requires new space, they're like, oh my God, if I change your email, you're going to save the whole document again? Well, that statement has a ton of presumption in it, right? It presumes that the only way you could possibly change somebody's email address is to store their entire document again. Who says that? It's not written down anywhere. It doesn't have to be that way. So one of the things we want to make sure is, when we grow our value, and we represent the process, which is what's new, that process is minimal, that our representation of novelty is minimal. It's as small as it can be. And one way to do it, I'm not saying this is the only way, but one way to represent novelty is to say we're only going to represent data as facts, and the only way we're going to represent process is as the assertion or retraction of a fact. And we'll talk a little bit more about facts later. And anything else that might happen in the world, we can boil down into that. We can represent that way. And that becomes really small. I now assert your email address is this. I don't care about your document. There is no document. And there's no more space required to say that than the amount of novelty. For declarative programming, I think this is actually the easiest part. We've already seen, this get added to Clojure and other languages like Datalog. We're particularly going to choose Datalog, but there's nothing that says you can have other or more query languages. The important thing, though, is we want this in the application. We want to move this declarative power inside the application. We also want it to be integrated with the rest of the application, as opposed to being sort of a dedicated system that only works about itself. We want to extend this programming so that it can apply to the data structures you have in memory and the rest of your program. So you want to make queries work on anything. And you want it to be extensible to user code. So this is the way it really becomes part of your application, so that it can call your code and vice versa. To solve the over there problem, we have to move the data to neutral territory. Right? One of the problems of client-server is it's based upon a model of hardware that's disappearing on us. Right? There were these servers. They were really expensive. It was expensive to get a machine with big processors and big memory and big disks. So it became a really important and rare thing. So sending the stuff over to the server made sense. Now, with SSDs and fast networks, the privilege of data access that was possessed by that server is no longer unique to it. It can be possessed by any machines. And therefore, moving the data out of the privileged control of a single machine becomes a critical underpinning to building a system where you have peers. And you actually can spread around your computational load and your data access. So we want no privileged access. This idea begs the question of, so what is storage? I mean, it's not actually a disk. There's not a lot of disks that you can connect multiple processes to. Now, there are SANs and things like that, and there are systems built around that, and that's a flavor of this idea, moving the data to neutral territory. But you can encapsulate the idea of a SAN and all of these concepts of data being over there and universally accessible in the idea of a storage service. Right? There's some service that has the storage. I don't know if it's 1 machine or 10 machines or 100 machines. I don't know where it is. I don't want to know anything. I just want to say, give me this block of information, and it says, here you go. And those services exist, and some of them are very capable. So we want to take advantage of these services. No dedicated machines, no special accessors. We can always superimpose that, right? If for some reason, for working set coherence, we want to have one machine only does the A's and one only does the B's, so we get more scalability. You can always do that over the data. You have to make an A machine and a B machine with the A disk and the B disk, right? You can make an A working set and a B working set and a storage service that everybody can access. You'll still get those benefits of locality. So you want to separate. And this is the same thing, right? This is the same thing we saw in Clojure. Most design is taking stuff apart. And we're going to call the applications peers. At the point in time that they have as good access to data as any server ever had, they're peers in the system. And the notion of a privileged server for this purpose goes away. So how can we take advantage of these scalable storage systems and redundant storage systems? The key is to actually separate reads and writes. Right? As long as you're doing update in place, there is a place. You're putting stuff there. If someone wants to see what has happened, they have to go there. If they want to see something consistent, they not only have to go there, they have to go there and stop everybody else. Right? Again, this place orientation is a killer architecturally. It just stops everything. You can't do much better than that. There are very complicated systems that try to pretend everybody has a writable database locally. That's update in place, but they're very expensive and very, very complex, and not really delivering a lot of these benefits. So we want to separate these two things. When you separate them, when you say writing happens over here, reading happens over there, you now can make independent decisions about the availability, consistency, scalability trade-off. And that's what Datomic does. It says, you know what, I'm happy with traditional scalability of consistent systems. In other words, I like transactional systems. I like transactional servers. I have yet to build a system that soaked the server. I know plenty of other people who are in the same boat. Right? The only way they soak servers is with queries, almost never with writes. So if you had a server that only handled writes, you would be able to accommodate a lot of business and other problems. So we segregate writes, and we use transactions for writes. And we have and we do only that there. And then what we do is that we have the output and the results of transactions be immutable. By making it immutable, we've solved the place problem. Right? If I want to see something immutable, do I have to go where it was first made? Could I go to a copy? Sure. A copy is just as good as the original place. So we write our stuff someplace where we can make many copies. These storage services generally are highly redundant. They keep 3 or more copies. And then we can read that a la carte from anywhere at any time. So now the consistency problem, you don't need transactions to deliver consistency for reads. You only need that because you were doing place-oriented programming. When you pull those two ideas apart, you can make a different decision. So anybody who says, oh, you have to do blah, you say, are you talking about place-oriented programming? Because that's not the only kind of thing there is, or could be. Once you have immutable data, you can move it around, which means also, once you've read something from somewhere, could you remember it? Sure. Are you going to worry about that? ooh, I wonder if this is still good. No, you don't have to worry about it. As soon as somebody's told you it's immutable, you can cache it relentlessly, as many places as you want, as often as you want, wherever it makes sense. So in this way, we get sort of both worlds with different trade-offs. We have consistency, which means, yeah, we have availability limited to availability for single server solutions, which can have hot standbys and the various traditional solutions. Then we can have real cool, modern, distributed storage for our reads. A little bit of both gives you an interesting system that's consistent and scalable on the read side and on the query side. For the flexibility, we're just going to remove the structure. Right? A good example of this is RDF. Right? RDF said, we can represent anything in the universe with subject, predicate, object. And they're almost right. That's almost right, but just build it up. Right? What's a fact? Sally. Not doing it, right? Sally likes. Still not really a fact. Sally likes pizza. Sounds like a fact. It's like, oh, that's good. That's a fact. Has she always liked pizza? Will she always like pizza? Now we're sort of seeing that's not actually a whole fact, is it? Maybe she was allergic to dairy, and then she figured out how to deal with that, and now she likes pizza. She started liking pizza at a certain point in time. Then maybe she becomes allergic to tomatoes, and she stops liking pizza. Right? Facts have time. So we have to become atomic, but we have to make sure we're complete. So we have our notion of this we just call a datum, mostly because the plural of datum with a U is data, and that's just a generic term that means nothing now. So we can have datums if we spell it this way. Also makes for a cool trademarkable name. Which will consist of entities, attributes, values, and some representation of time, which I'll talk about on the next slide. But the fundamental thing is, if it doesn't have time, it's not a fact. It's as incomplete a fact as Sally. There's something not there. Okay, so how do we deal with time? Well, one way would just be to put like a time of day timestamp on every fact. But it ends up that, as you'll see in the rest of the system, because transactions are serialized, they're as good a universal timeline as anything else. And then, so we can instead put on the datums, instead of putting the time of day, we can put the transaction they were part of and associate the time of day with the transaction. As soon as you do that, you're like, ooh, if I could associate the time of day with the transaction, I might want to associate, who did it, or what process did it, or where did we get this information from with the transaction. You say, you know what? There's not a good reason for transactions not to be first-class entities. So do it. Transactions are first class. And time is just an attribute of the transaction, as could be other things. And then you get to the critical point, right? We talked a couple of times about basis. You now have a notion of a basis for computations, which is the database value at a point in time. If we can figure out how to deliver that, we really can deliver the time promise. And it was an objective of mine in this design because I've made a lot of systems in the past that had to manipulate time. They had to keep everything. They had to keep the time of everything. Right? Anybody ever write a system like that? Right? You start adding timestamp fields or whatever. How is that query for finding the latest value at now? You like that query? How's that perform? How many people have tuned that query? Yeah, that's hard. That's really hard. And then, once you've built a system that has this, what do you end up with often, right? So much of your system needs now, right? So you build a whole bunch of your system that's now, right? Because now is, like, you can't say what now is. You just sort of, I want to ask a query, I want the freshest answer. So now you have processes and methods in your program or functions, and you have stored procedures, right? They're all like the now ones. And then somebody says, okay, well, we stored all those timestamps so that we could do historical work and auditing. I want to ask those same questions as of last week. And you're like, oh, now I need another version of all of that parameterized by time. And I have to go into all my joins, right, and flow around that time basis. I've done that. I think that's incredibly difficult to get right and does not perform well. So the idea is, instead of saying, make a time a parameter of everything, if instead you could say, look, just give me the value of the database as of last week. If there was some way to do that, then the same queries and the same programs could just be handed last week's database and would work the same. And that problem about that bug we had before we had a certain amount of data, we could go back and look at it. When was that happening? That was happening at 11 o'clock. Give me the database as of 11 o'clock. Let's see it. Oh, look, there's the problem. Here's the problem in our code. It's fixed. The next time, that won't happen to us. So we're going to shoot for that. As far as perception and reaction, the idea is we've reified process. Right? Whatever we say, however we're going to represent change, we're going to be able to push it around. And that's all we're going to do. It's going to be data, and we're going to push it. Right? Once I've pushed you some data, you've got a query engine that can query arbitrary data. If you want to react to specific things, what do? You just query the novelty. And you can do that. It ends up that the novelty alone isn't enough to answer all the kinds of reactions you want to have. Like you might want to see this stuff was new and what was the basis for it, or this stuff was new and where did it take us. So it would be nice if we could get the values of the database before and after the process event. So that all sounds good. How do we do this? This is the overview of the architecture. And this is the full production system. You can actually, because it's all defined in terms of protocols and whatnot, you can fold this up and run it in a tiny in-memory thing. But the logical model is this. Your application is a process. It's going to incorporate a library, which is going to empower it to be a peer. That library is going to have some communications bits, obviously, because it's got to talk to the service parts of the system. It's going to have a query engine. I'll talk a little bit more about the live index and caching. But that goes in your application. Then there's this dedicated machine, or it could be a set of machines acting in standby for each other, called the Transactor, whose job is only to handle transactions and writes. Right, so we said we're going to split reads and writes apart. And we want a consistent world, so we want transactions. So essentially what a transactor is, it's like a database server. You took away their query. You took away their, well, they can do internal query, but you took away their serving queries for others. You took away their serving reads for others. You took away their having to manage storage explicitly. And what they were left with is handling transactions and some occasional background indexing. And so that's all the Transactor does. It just coordinates transactions. It accepts all the transaction requests, serializes them, and puts them in storage. And finally, you have this storage service. DynamoDB is the first one we support, but it's an example of a storage service. You can look at a lot of things. There's the Riak guys out there. I hope someday we can work on top of them. They have a really good storage service. Right? It's a service. It runs as a cluster. It's redundant. It's distributed. It has all those great properties of Dynamo. The idea here is if you built it on a service model, the interface to the service, as I'll talk about, is actually pretty small. You can make independent choices. Again, you're moving away from something monolithic. You're going to end up with more choice. Choice about location, choice about scale, choice about price. But Dynamo is an example of a storage service. And we put off all the actually sticking bits on disks on this service. And the peer, as you can see, can directly read back from the service. So the Transactor will put stuff in storage. The peers will read it right directly from storage. They don't read it back from the Transactor. The only interesting thing the Transactor also does is you'll see this line back from the transactions to the peers. It also reflects the process. It reflects the change back to any connected peers. And we'll see how that works in a second. So that's the overview of the architecture. So the first problem we encounter in trying to represent this is how do we represent this immutable expanding value? What's the data structure for an immutable expanding value? It's tricky, right? The first thing is it has to be organized, right? I think a database, why is a file system not a database? Or is it a database? I don't know, most people, when they buy databases, they're not like, oh, now I can replace, XFS with this database, or vice versa. Right? Usually a database adds some more value to give me whatever is stored at key or file name X. It's organized. It's organized in such a way that it can help you leverage the information you have. One way to leverage the information you have is to support queries, for instance. So we want organized state. And we want it to be expanding. So one representation of that is a sorted set of facts. Meets this criteria, right? your email was this, your email is now that. Because those have times, we can just add more facts, right? You change emails, you like new foods, just add. So we have that additive process because facts have timestamp. They're going to be different from each other. But they have to be sorted in order to support query. What everybody has discovered in the past, and Bigtable is an example of a solution to this, is that sorting live into storage is a bad idea. It's too expensive, has tremendous overhead for the actual write volume, the coordination, and everything else. And it's like place-oriented programming at its worst is actually maintaining a sorted index live on disk. So Bigtable, the design is really simple. It says you should have a bifurcated system. You should accumulate novelty in memory and periodically merge it to disk. And then you can keep a sorted version of things on disk. And Bigtable does this with big flat files. And what they say is, in order to see a sorted view of the world at any point in time, you're going to have to merge. You're going to merge your memory view with your periodically created storage-based view in order to get a coherent view of now. So this merging is an efficient way to do this, and Bigtable is a great example, and it was an influential paper for this design. So you want to accumulate novelty in memory. You want to occasionally merge it into storage in a sorted manner. The difference between what Datomic does and what Bigtable does is Datomic uses trees, unsurprisingly. It uses, because what we want in memory is not some mutable thing. We want an immutable thing. We know the right way to represent that is with a tree. Similarly, in order to get the caching and addressable characteristics you want from putting your data on storage that the peers can access, you really don't want gigantic flat files. Right? It's hard to say, I've cached this portion of this flat file. And it's hard to do multiple indexing jobs and have any portion of that caching you did still be valid because the files sort of slid around. If instead you store a tree of nodes in storage, then I could remember this node, and if that node hasn't changed in the new indexing job, I can still remember it. So we use persistent trees in memory and persistent or durable persistent trees in storage, and basically implement the same idea. Accumulate in memory, periodically merge into storage. So what goes in storage? Obviously, novelty comes in. That has to be recorded right away if you want to meet ACID. Right? It has to be durable before the transaction returns. So there's a log created of just the asserts and retracts. It's, again, unlike traditional logs in that it's not one contiguous file. Again, that whole idea of one contiguous file, that's super oriented around spinning disks on one machine. That's ending. It's just over. So there's no reason to do that. A better representation is a tree, again, for the same reasons. Caching, locatability, and things like that. So we log directly into storage. The other thing that's in storage are these index trees. And they're covering. In other words, each datum is entity, attribute, value, and transaction. Every index is a sorted view of all of that. So it's not really an index like an index that points at something else. A covering index has all the data you need inside it. So it's basically multiple sorted sets of the data, sorted in different ways, as trees. Because we want this to be to work with services, you want to minimize the footprint of an API you use to talk to storage. And so in our case, what we're fundamentally based around is a storage that essentially implements key value. Right? We're not going to use the values to store, pizza. Right? That's too tiny. We're going to use the values to store entire segments of our index trees. So essentially, we're using it as keys to blobs of index storage. Much the same way that a traditional database would store blocks of its B tree on the file system as blocks. We store blocks in the key value store. But it ends up that fully implementing the state model requires something a little bit more than just give me what's at this key and value, potentially inconsistently, which is the way a lot of these key value stores work. In order to emulate atoms, which is part of the model, we need consistent read, optionally, from these storage services. We need to be able, when required, to ask for something and make sure we get a consistent value back. And a lot of the systems can do that. You can just, by turning up the number of reads you issue on a request, you can ensure that what you get back is consistent. The trickier thing, which is less readily available in key value stores right now, is conditional put, and this is used by the Datomic storage engine for the moral equivalent of pods, which I'm so reluctant to say that word, but effectively that's what Datomic has inside of it. In order to accumulate log, you need something that allows you to build up the tail of what's going to become the new part of the tree. If you look at the inside of closures arrays, vectors, that's how they work, right? They build up a tail, and only when the tail is full do they pay the cost of merging it into the tree. So you need something like that, and in order to do that, potentially safely from dealing with multiple transactors succeeding each other, you need conditional put. This is something that DynamoDB has. It's something I'm looking forward to being present in more of the key value stores so that we can work on top of more of those. So index stores look something like this. You don't have to read the details, but it's a tree, right? Up at the top, there's a root that has, the datum sorted by entity, then attribute, then value, then time. Then the same datum sorted by attribute, then entity, then value, then time. Potentially a reverse index for any reference-based attributes. We also do Lucene. We keep in the same way. And then there's a 3-level tree, a root, an intermediate set of directories, and a set of data segments. Inside each data segment are sorted datums. And it's those segments and those tree segments that we put into storage, entire blocks like that. That's the granularity of what gets stored. A database value is essentially a pointer to a couple of things. It's a pointer to the live tree in memory, which represents everything that's happened since the index on disk was made. So you have a persistent in-memory sorted set that you merge with the one off disk. So you have a pointer to the memory one, a pointer to the disk one. There's a lot of other subtleties in there with history and things like that. But the fact is, the disk-based one is lazy. Right? Obviously, you're not going to pull the entire universe off storage into your process if you don't care about it. So effectively, you have a proxy for the storage engine sitting there saying, if you ask me for something I don't have, I'll go get it. I'll pull it into cache. And then manage your working set in cache. And the cache is hierarchical. I'll talk about that, I think, in a second. How do we do process itself? Well, one of the things is asserts and retracts can't actually express everything. Right? I can't increment with assert. Right? If it was 42 and I want to make it 43, I can't just, I could do the calculation somewhere, but I can't express the calculation by saying 43. So we have another notion of what constitutes part of the input to a transaction. It's called a data function. It's actually a function of the entire database inside the transaction, plus any arguments. And what it outputs is another transaction segment. So a transaction can consist of assertions, retractions, and data function calls. And data function calls, in turn, will be passed to the database and can return assertions, retractions, and data functions. And we expand and splice in the results until it's all asserts and retracts. So it looks like this. Right? You can have a transaction that was assert, assert, retract, a call to the data function foo, retract, assert, assert. And then foo could have expanded into calls to data functions, bar and baz. And bar and baz could then in turn expand eventually into assertions and retractions. What does this look like? Macro expansion. That's right. This is the process version of macro expansion. But it's really cool because you end up with these primitives. You do end up with a primitive representation of process on which you can build something that allows you to do transformational updates. We talked about the transactor, right? It has a couple of jobs. It accepts transactions. Those transactions look like what I just showed you. It does the job of expanding them. It will apply them to the in-memory version of the database. If nothing bad has happened, then that's a successful transformation of the database, at which point in time it will log it to storage and broadcast it back out to the other peers saying, this happened. What gets broadcast are the final assertions and retractions. So the peers don't have to do all the transformations again. They just get the answers sent to them. And periodically, the same transactor will do indexing. That's something we could move to another machine, but right now the transactors do it. An interesting thing about this system, though, again, you're seeing parallels, I would hope, constantly to the memory version, is that indexing, right, is going to create at least a new root, probably some new directory nodes, and definitely a whole bunch of new data segments. What about the old ones? They're not getting updated, right? So where are they? They're still sitting there. They're now garbage. So you now have garbage collection and storage. It shouldn't be surprising you have analogous things happening in storage that you had happening in memory. And there's no problem with that. So there's garbage, and there's garbage GC, storage-based GC that cleans it up later. When no one ever cares about that root anymore, it can go away, or on a time basis. Declarative programming we do by embedding data log. A couple of things about doing data log well for this purpose, especially for having a different basis. It's typical of languages like Datalog and Prolog that the database is kind of ambient, like you're just writing these things and it's as if the database is always there. But that's essentially like global, which means you have no way to like talk about, I want to issue this query on this data. So we have to make sure that both the data sources for queries and the rule sets that are used in queries are arguments to queries. They're not ambient and not global. Right? When you ask a query of SQL, do you get to say on what version of the data do you run? No, it's like whatever's happening right then. Your query runs right then in the middle of the server, whatever's happening. It's always now. So if you want it to be other than now, it has to be an argument. So they're arguments. We've extended data logs so it can work with scalar values and collections in memory and things like that. And you can extend it with your own code. So now we don't have the over there problem. Now we have over here. Right? We can directly access storage. We have our own query engine. We have this live index. Right? When the transactor pushes process back out to us, we update our own in-memory index. So just like the transactor is accumulating an in-memory index, and then eventually it merges it with the storage one, a peer is accumulating the same in-memory index and referencing the same stored one until the transactor says, I've made a new stored one, and you can drop what you've been accumulating in memory and move over to that as your stored one, and we start from scratch here. So just build up a window of stuff, merge it, then drop it, build up a new window of stuff, merge it, and then drop it. That's how it works. Inside the peers, there's a two-tier cache. Right? Eventually you end up with a ton of datums. And you can really overwhelm your Java heap by having like a gazillion objects as your cache. So we instead have a two-tier cache where stuff we've already pulled from storage, we actually keep in the lowest tier of the cache as compressed index segments that look to the Java heap as if they were just byte arrays. And only in a higher level of the cache do we turn them into thousands of objects. So there's a level that's thousands of objects or millions of objects, and then a level which is compressed, indexed, not yet expanded guys. And it's faster to just expand them than to go across the network to recover them. So you have these two tiers. One's on heap and one is potentially off, but at least it's not high pressure. So we're now starting to get the consistency and scale stuff we were looking for. The writes go through the transactor. It has a traditional model of scalability, right? It can scale as big as one machine can scale. But that server is no longer burdened with any query load or read load. It's not indexing live on the same cores that it's using to serve transactions. And it has a traditional availability model. You run hot standbys. And they're easy to run because their reference data is not like a live connection from the other server. It's the storage. So it's very easy to transition from one to the other, and you don't have to have these complicated shoot the other guy in the head relationships between streaming servers. The immutability is all we need to support consistent read. So we get consistent read, but we also get scalable consistent read because we can now use these highly scalable redundant storage services, which is really a great combination. That's sort of it's what Datomic is about, is getting this combination of features. If you don't need transactions, it may not be the right thing, but if you do, it's an interesting combination. And query scales with peers, right? Your computational load is now in a peer. If you want to run a long-running query and you have your own box, okay. That computation is not interfering with other computations. So having a set of peers that just do analytics is not really in anybody else's way, which is part of the objective. In terms of the flexibility side, what do we have for schema? Well, we boil it down. We said, we're going to store these little facts. And in fact, that's the end of the representational structure. There's no other structural things. There's datums. That's what we store. So the only thing you do have to encode are your attributes. And it's important that you do this, right? There are systems that say, just stick in whatever you want. Just put any text. We'll just take all your text. And they redundantly store all the text. They they take all your typos. They don't understand the types of things. It's not really that great as a database. It's worth spending this much effort to say, you know what, the name attribute is a string. And the time of day attribute is a date. And the other thing is a time. And so you have to tell us the name. I didn't even put type on here. Name and type. And then cardinality. Cardinality is a really interesting problem, right? Think about your typical database. How much different is it to say, Fred has a new email and Fred has a new friend? It's different, right? Why is it different? I don't know. I don't think it's a good idea that it should be different. I think it should be the same. So that's what we support. You tell us what the cardinality is, and if you tell us email is cardinality 1, when you say Fred has a new email, that's the email we're going to return when you ask. If you say Fred has a new friend, that friend will be included in the set of friends we return when you ask. And that's how I think it should work. Think about a relational database. What happens with those two things? Well, email may go right in a record, but friend definitely has to go in a different table, right? Even in a document store, same kind of problem, right? Email is like directly in the attribute, and friend is in what? I don't know. If it's JSON, it's in a list, right? Which means that making that change to add a new friend means changing that list. That can become precarious. And that's why things like Redis have smarter primitives for that, because that's ugly if you don't do that better. Another notion of an attribute is whether or not it's a component, right? Your arm, if it was a separate entity, is a component of you. Your grandmother is not. Your grandmother is so both are entities, possibly, depending on what you're doing. But one is definitely part of you. If you were to go away, your arm would go away too, and the other is a relationship. So we want to know that. We deal with uniqueness. We also have a way to talk about things by name, which matters. Effectively, it gives you multi-maps. So for time, we talked about this a bunch of times, but the database ends up being a value. You can issue queries across multiple databases, a database from the past and a database from now. But the critical thing is you can take a database and say, given this database, I'd like to see this database as of 2 weeks ago. Once you do that, you have another database value you can place into a query and get answers as of 2 weeks ago. Similarly, you can do since a point in time. The other thing we can do is we can do as if. Right? You can ask for this database with this transaction applied, not going through the transactor. It's just a value transformation. What would this database look like if I issued this transaction on it? It lets you do what-if stuff without interacting with the rest of the universe or interfering with it, which is really a big deal. And there's also an efficiency thing here in how we deal with time, in that we move the past, any retracted past, into a separate index, so it's not in your way. Finally, for perception reaction, this is actually straightforward now, right? We saw there's already a live feed of process from the transactor to the peers. You can basically just tap into that in your program and say, I'd like a queue of those process events. And then you can take them. What we passed actually is the process event, the database before it, and the database afterwards. And you can issue any queries you want in order to trigger any activity you find interesting. So, to summarize, I think the state-time identity model should be familiar to this audience. I didn't set out to make it the same. I wanted to make sure that I just answered these questions. It ended up being the same, which I think is great. But obviously, state-time identity is not enough to solve the database problem. You need this process, and so that's what you add. You add a reification of process, an ability to manipulate it, an ability to get values of databases. From a technical standpoint, that dynamic merge thing that Bigtable does, it's essential. You cannot store persistent data structures on disk live. You can try it. You can technically do it. It will always perform terribly and use up a ton of space. So it's a good idea that we copied. The other thing is just, again, how many times did I say immutability in this talk? Immutability rocks. It's one of the things that's very interesting about it is you cannot represent change you can't correctly represent change without immutability. It's a profound idea. It's not my idea. I think it's just some essential characteristic of the universe. But it really needs to be recognized in our architectures. And so if I had any recommendation to you at all, it's just, if you think about designing a system and you're not sure you can answer all these questions in the forward direction, choose immutability. You could almost back into a little bit more than 50% of this design just by having taken immutability as a constraint and saying, oh my God, now what am I going to do? I'm not allowed to change this. I better do this. It will keep forcing you into good answers. So if I had any sort of architectural guidance from this, it's just do it. Choose immutability and see where it takes you. So that's it.